Welcome to 6.8 Trapezoidal Approximations Summation Notation. I know some of you are going to be pretty excited about getting to this because I accidentally gave you one of these problems earlier this week. For most functions, using trapezoids to approximate areas is more accurate than using rectangles. So we have the area for a trapezoid as being listed 1/2 the height times the bases being added together. So most of the time when you looked at a trapezoid, it looked like this, where the base was definitely longer. The bottom base was definitely longer than the top base. But that won't always be true, okay? And so just wanting you to know, yes, sure, this distance from here to here is h, but what if this guy got cut off and formed a right angle? Well, guess what? That's still a trapezoid. This is still my base 1, and this is still my base 2, even though I have a right angle there, okay? Not only that, but what if one of my bases had a height of 0? Think about that. I have a base that is a height, but then I have another base that is no height at all. Well, what would that be? Yeah, that'd be a triangle. So, I mean, right? If I turn this one into 0, then it would be 1/2 the base times the height. Or if I turned this into 0, then it would still be 1/2 the base times the height. You see what I'm saying? So anyway, now that we recognize trapezoids, you want to do 1 here. Let's try this. Let's call this 3. Let's call this 4. Let's call this 1/2. And so I'm saying that I have the area is equal to 1/2 times that 1/2 height, right? This height is 1/2. There's also a 1/2 there. So I got 2 of those. And then the 2 bases, let's add them together, 3 plus 4. So I end up having 1/2 times 1/2 is 1/4 times 7 is giving me 7/4. Okay, so that's how you do this. Only more likely we will see something like this height and that height, and this is my width, but I still want to use the trapezoidal rule, so he's changing it into the width of the subdivision times the 2 heights that you have being added together, which reminds us, I think, of lesson 6-7. And so that's why we taught lesson 6-7 that way, so you could see it that way, okay? So they're usually positioned vertically. We've got our formula. We're approximating the value of a definite integral using these trapezoids, using the same strategies we had in those Riemann sums. We're adding areas of trapezoids instead of rectangles. So here we go. I'm going from 0 to 10, and this graph looks super familiar, except he's obviously made up some weird subdivisions here for us to try these trapezoids in particular, all right? So the integral from 0 to 10 f of x dx is going to be equal to, and I'm going to throw a 1/2 out here for this first guy. I have a width of 2, and then I have a base of 0 plus a base of 4. And so again, I'll mention, I wish that this side had a distance, but it doesn't, so I'm just calling it 0. And then I'm using this side, is this side right there. And then this remember, is that height, or now I guess we're calling it width. Okay, so then that was just for number 1, for trapezoid number 1. And then I have 1/2 times that width of 4. So from here to here, he's really making it clear that it's a width of 4 for us. Nope, my bad. Yeah, wait, what? Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's a width from 2 to 5 is actually a width of 3. I wonder what these numbers down here are. Are these supposed to be helpful? These are terrible. Well, now we know, okay? So I did do this one correctly though. Okay, so then the width here is from 2 to 5, which is a width of 3. So I'm going to put that in there, 3. And then I have my 2 bases. That's this guy and this guy, which is a 4 and a 3. And that is not an accident. That's why I used that up above. Okay, so then this is a height of 3 and 2, and this, by the way, is the second one. And then I'm adding the width of the third one, 1/2 times this width is 1, and the two heights are going to be a 3 and a 2. And I'm just erasing that because it's not part of this. And then a 1/2, and that's the third trapezoid. And then I have the fourth trapezoid, which this width is from 6 to 8. So that's a width of 2. And then I have these two heights, which is a 2 plus a 2. And then I'm doing, let's see, then I'm doing that was the fourth one. And then the fifth one is going to be from here to here. That's a width of 2. And then the two bases are going to be a 2 and a 5. And I know you want to work this out, like I get it. You want to know exactly what this is. Put it onto the calculator, check it, okay? Do it yourself, put it onto the calculator, see if it works. Pause here. Good job, I believe in you. Okay, ask me for help if you didn't get the right answer. Note, the area formula for trapezoid also works for triangle where the heights were 0, and we just mentioned that right here, that height was 0, so that's cool. If you forget the formula for a trapezoid, you can always draw your areas as rectangles and triangles and not even use trapezoids. You could also average the values from a left and right hand Riemann sum. In any case, make sure that you show a clear setup. That's always essential, okay? And so example 2 says use these trapezoids with 4 equal subdivisions to approximate those areas that are shown. And notice again, we have a table here, and it's totally possible for you to start, using that table in any way that you like. The area of this guy is going to be 1/2, and I am sick of writing 1/2s, so I'm going to do that at the end, right? And then in between, though, I'm going to say that I have these distances here, and that's 10. And look at that. Well, you know what? I'll tell you what. I'm going to throw that 10 out in front, too. And now what am I going to say? Well, then I'm going to add these bases together, and I'm going to get the answer. So this one plus this one, and then this one plus this one, and then this one plus this one, and then this one plus this one. Are you noticing that I'm hitting that one twice, and that one twice? Because you should notice that. That is part of the pattern, okay? And so I'm saying that I have my 1.8. That's this guy and this guy. Well, the 1.8, sorry, plus 2. And then I have the 2 plus the 2.5, and then I have the 2.5 plus the 3.5, and then I have, oops, plus sign. Yeah, if you forget the plus sign, it's all wrong. 3.5 plus 2.2. And ta-da, that would be your answer there. Again, I encourage you to go put it into a calculator. Try to do it by yourself, and if you can't, then put it into the calculator. Ask me for help, okay? As the number of subdivisions increases, the accuracy of a Riemann sum approximation improves. To achieve perfect accuracy, we need to approach infinitely many subdivisions. This is going to be a limit, okay? The limit definition of the definite integral. So we had the limit definition of the integral, which was the limit as h approaches 0 of f of x plus h, minus f of x all over h. And we learned that taking the derivative was a process to kind of shortcut all the work of this particular limit. Why would we want to go back to a limit? Well, we're just trying to prove that everything that we're doing makes sense. All right, so it's a pretty complicated formula. I feel you. I guess we want to put it on the mega cheat sheet. And you know what? I'm letting you know that this topic might be new. I know a couple of changes have crept in the last couple of years, and I've been having trouble keeping track. So I haven't taught this in golly like forever. I used to teach it because it's definitely a part of BC, but I had not seen it in AB. in many, many, many years. All right, so here's what I want to focus down on then, is that I am going to take my function and I'm going to plug in that. And you're like, well, what is that? Well, the k will stay there because it is part of this, that I'm going, it's my it's my counting variable. And so there will be a k in the answer. And then a is this lower bound. This is going to be my lower bound. So as long as I could see that lower bound, I could throw that in there real quick. And then this delta x is supposed to be the same thing as my dx, right? So I usually write that as a dx right there. You could see it. And so how are we going to calculate that dx? That's the width of the subdivisions, which I have already taught you this formula. I did it in the last homework. Do you remember where I said you take the end minus the beginning, and then it's going to be over the number of subdivisions? And what did you get? That's how you got the width. You remember that formula I was teaching you? This is it in a nutshell. It's exactly the same formula. All right, so I know you love me now. All right, here we go. So we're going to do this integral, and we're going to say this is the limit as n approaches infinity, and we're going to do the counting thing. K equals 1, and here we have n. Oh, my summation symbol. It's called a sigma, and I don't know how much more it's going to get used on this test. So you'll use it more when you get to Calc 2. And then he says, let's plug this thing into f of x. Well, I'm trying to figure out what that thing is. Ready? That's a. So I'm going to say that it's 1, and then plus a k, and then I'm doing this b minus a over n business. So I'm doing 4 minus 1 over n, and that is going to be what b minus a over n looks like. And so I'm going to do k times 3n. And then they said, throw that into the function. Well, that's the function, so I'm throwing it in there. And that's how we get that. And then over here, I have to put another 3 over n, because that's just part of the formula right here. As it says, do it twice. Okay, so now I've got that. Now you see what that looks like. Okay, I bet you would love it if I did just like another really quick one. So here's another quick one. All right, so let's say that I'm going from 3 to 10, and I'm doing x squared dx. Do you want to try it? Pause. Okay, the limit as n approaches infinity, k equals 1 over n, and then I'm doing, ready, the lower bound plus, I'm doing the k, and then I'm doing that b minus a over n business, which is going to be 7 over n, and then there's going to be an squared, because I had squared, and then I'm going to do a 7 over n on the outside as well. And that is the answer to that one. Ta-da! Now, what if you had to go backwards, and probably more likely that you will, then we want to come in here and see if we can't sort this out. So, for example, I know that that's a, so this is starting nicely. I got a pi over 2 here, and then I noticed that the b minus a over n is the same thing as pi over n. Well, I just figured out what a was, so I can plug that in. So ready, I have b minus a is pi over 2, and that should be over n. And then, all of this is over n, and then that equals pi over n. And I know it looks like a mess, but let me just mention, do you see how this is the denominator and this is the denominator? Well, it turns out I'm not trying to solve for that. What I want to solve for is b. N was going to be in my equation no matter what. So I'm just going to focus on the top half, and I'm going to leave off the bottom half. Like, can you do that? Are you allowed to do that? Sure. Let me talk about it like this. What if I had this? 1 minus 4 over k equals, ready, 6 over k. Well, my bad. I need there to be a variable up here. All right, b, like that. Okay, so there you go. So there's a variable up here. And now I'm just saying forget this. I'm just trying to figure out what the b's are. You see what I mean? B minus 4 equals 6. Well, b must equal 2, you know? And then I can put it back into my equation and I'll have some k's in it. All right, so I was just trying to say, I'm just focused on this part. And now what do I have? I'm going to add a pi over 2 to both sides. And I end up finding out the b equals 1 pi plus another a half of a pi, which means that I have 3 halves of a pi. Now I'll show my work here. This is the same thing as 2 over 2 pi plus 1 over 2 pi. And that means that I have 3 halves of a pi. All right, so that's what b is. And so I'm coming back over here and I'm saying this is 3 pi over 2. And then I'm going to write down, oh, look, I threw it into a function. The function that I threw it into was a sine. And then I just put down the x and the dx. Because remember, I'm trying to go backwards, right? I'm trying to go backwards. I'm just trying to go figure out what that original function was. And all of this stuff is what I plug in the place of x. Let's see. Do you see what I mean? So I have f of x over here, and I'm basically replacing x with just that business. So I'm taking this business back out, and I'm putting x back in, and that's my answer. Now, here's what his note says. It says, other shifted answers are the same. And he had one. Let's see if I can't find it again. Hold on. Oh, yeah, he had one, and it was this guy right here. He says that this one is going to have the same answer. And I don't know, you know, why he would mention that. It feels kind of mean right now. But let me just talk about the concept of it, okay? And it does matter because we do this later on as well. So sine, I think you know that it repeats, right? And it repeats over 2 pi. So this would be 4 pi out here. And I think it's obvious that if I was doing something like, you know, I feel like I mentioned in a previous problem that like these two areas sort of cancel out. I have the positive version and the negative version of them. Okay, sure, but like that area would literally be the same area as this. And so I'm adding a 2 pi to it. So sine of x is the same thing as sine of 2 pi plus x. Then these things, this is a fact. These are true things. Okay, so not just that though, I wanted to say that if I zoomed in on sine, here, let me draw it using this line. It's very handy for me right now. Okay, so if I, go right here, so this is 2 pi, this is pi, well, say that this is pi over 2. If I take this area to the left, it would be the same as the area to the right. You know what I mean? And so it looks to me like he's incorporating that pi over 2 shift into the function, and then he's changing the limits of integration to match that shift. So if you have the pi over 2 in here, then you take away a pi over 2 from there, and you take away a pi over 2 from there, and that's how you end up with the 0 and the pi. So it's interesting. I don't know how you're going to use it, though, okay? And good luck on the assignment.